Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program. Previously on Saturday Morning Physics.
If you change the length of the string, which I can do by just touching a piece of the string and holding it, you could change the tone that you got. This is a flame tube. We're going to actually drive sound waves down the tube and then see if we can observe something. And then we'll tune the frequency and see if we can find the standing wave modes in our pipe. That's pretty good. So there's 4 loops. A little more amplitude. Yes! Here's the pipe, open-end pipe, nothing strange. And if I just blow air into it, you'll hear a tone. And if I close one end, you'll hear it go down by an octave. Now this pulling business that I wanted to test, you can see what the implication is that as I blow a little harder around one of these places, I will tend to have the tone shifting up and down a bit. And so, for brass instruments, you might think are really different from things like clarinets and saxophones, but actually, conceptually, they're not so different. They're actually a reed instrument, and the lips are the reed. So you see it's just an opening, and then it terminates in a tube that can plug into our instrument. Here I have one from a trumpet. The trumpet one is smaller. That's because trumpets play higher tones, and so you have to make the vibration faster, and you've already learned that smaller things tend to go with higher pitches, and that plays out also for these kinds of devices. So in our general logic, we've talked now a little bit about how you have to make a sound. We've talked a little bit about the interaction between how you do it and what goes on with the wave. And then, of course, we should talk a little bit about how do you vary the pitch. If it's not an organ pipe where you just have a whole bunch of different pipes for the different tones that you want, but if you want to have an instrument, you have to have some way of changing the pitch. And we have to therefore vary this fundamental, the lowest one that tells your ear what the sound is. And so we have to vary the geometry. So one way to do it is to have tubes with holes. And so we vary the geometry, get multiple notes. Recorders, flutes, piccolos operate in this way, and also clarinets and others. The basic principle is really simple. The holes tend to force pressure nodes. The hole, if you make a big one, opens up the tube at that point and makes it so that the end of it is now like the place where the hole was. And that effectively shortens the length. So that's the concept. Here's a little sketch of how this might go with no hole. The tube is this length and would have a certain lowest mode. If you put a really small hole, maybe I should have made a smaller one there, you can imagine that a teeny tiny hole really won't do anything. On the other hand, if you have a really big hole, then that is essentially just as good as having an opening here. And now the effective length is the dashed line. And then you can imagine that as you go from this situation to this situation, you'll gradually change the effective length of the tube to being shorter and shorter until you finally get to that situation. And I have something to try to show that to you. So this is an organ pipe. I probably don't actually have to put this under the document camera. I think you kind of see that this is an organ pipe with a slide, and at the one end I have no holes, and then I have a series of varying holes until it gets quite big. And so what I propose to do is to play my way down. I have to blow very gently, otherwise it jumps up to the next mode. And now I put a little hole in. Because I'm effectively shortening the length of the pipe, I'm making waves that are shorter, and so the pitch goes up. Well, we don't usually make musical instruments with little slides that we push back and forth, but we do clever mechanical things that try to take advantage of that concept, and that's exactly what instruments like flutes and clarinets do. Because you have to be able to do all that with a set of fingers, then they're kind of mechanically complicated. I don't know terribly much about these instruments, but I do just show you blow-ups so you get some feeling for the kind of things. And if I turn this sideways, you can see the openings above the holes, and then you can picture these guys going closed, and various fingers, and so they're kind of complicated. For example, if I twiddle one of these, they both twiddle, and the flute players in the audience will be snickering because I obviously don't know details about what I'm doing here. But you get the idea. I'm looking for somewhere something complicated will happen, so that just to get a feeling for the kind of complexity, that I know that there's one that if I push it, about 4 of these keys go up and down, but I might not be able to find it for you now. But I think that I just want to communicate sort of the concept that we have with such a kind of an instrument, and then the players have to learn what keys to press in order to make some systematic thing happen. Here's a clarinet. You see this is a similar kind of a situation. Again, with holes, places to put your fingers, lots of levers and little gizmos, so that this one has a little rod that runs all the way along and activates stuff way down here. So they're complicated, but people over the years have figured out how to do that so that players can then vary the pitch that they get from their instrument with this complicated series of holes. So that's one of the basic methods that we have for varying the pitches of instruments. And again, it's simple. Knowing about these nodes, we just manipulate the waves inside by poking at them in various ways to get them to do what we want as much as we can. So there's another technique that you can use, and that's to try to really change the length. But instead, to insert extra length. So here, for example, is a trumpet, and it's arranged so that you have an extra length of pipe, which can be made inserted in the flow by pressing a valve down. So these are just little air switches. Here's a little bit longer length of pipe and a yet longer length of pipe. And so by putting in various ones, by pressing down various of these, you can make the length of your instrument go up. So as you make the length go up, the wavelength will go down, and that in turn lowers the frequency of the note. And so again, I'm not going to try to play this, but I can come with my dot cam just to show you. Just to show you the trumpet, and maybe I need to zoom back out just a little bit, but not too much. So here you see the middle one of these tubes that's inserted. Here, the short. So this is the shortest one, and this is the next longest, and then there's quite a long one. This is on the back side here that you get with the third valve, and then as the valves go in and out. This is my daughter's old trumpet, and the valves don't work so well anymore. But so that's the concept. And the instrument that I once upon a time knew and loved, which is the trombone. I still love it, and I know it a little less, but I can still make a sound. And the concept is pretty simple now. I'm going to move the slide out. That increases the length, and the tone goes down. Well, I'll start a little higher. So the nice sound you get from trombones, but the concept is still the same, that we're just messing around with the geometry of the instrument, changing its length, making the modes that are set up inside have longer wavelengths or shorter wavelengths, and that then changes the pitch of the instrument. So that's the basic method that runs through all these different instruments. Now I point out because you can see them here, that the flute and the clarinet actually have quite similar lengths. But you will know, I think, that flutes play higher than clarinets. So even though the lengths are very much the same, the clarinet plays 1 octave lower than the flute. And you might think to yourself, this guy's telling me lies, because he's just telling me that when things are the same length, and if the kind of wave is the same, namely an air wave, so the velocity is the same, then they ought to have the same pitch. So why, we could ask. And I already have planted the seeds for this, at least in your mind, and we can explore this a little bit. There is a distinction between edge and reed excitation that I didn't really point out to you very much yet, but it matters. Edges produce pressure nodes. So edges actually act like open pipes. That's things like the flute, and they make the end of the pipe where the mouthpiece is act like it has a pressure node. Reeds, on the other hand, because they have the reed closing and closing and closing a lot against the pipe, make the clarinet act like a closed pipe, and that makes a pressure antinode. And so if you remember the difference between open and closed pipes, this one has a lowest frequency, which is V over 2L, and this one's V over 4L, and the difference of a factor of 2 here, just like I showed you with the pipe being open and closed, causes the clarinet to play 1 octave lower. Even though they have the same length, they have a different end condition imposed by the kind of an exciter mechanism we have, an edge-like thing or a reed-like thing. So the clarinet has this closed cylindrical bore that makes its wavelength longer, so it plays 1 octave lower, even though the lengths are similar. And now I have to come to one other topic, which I've inserted here in my list. We've sort of put a bunch of holes in to show you how you could get maybe 7 or 8 or 10 notes, but that isn't as many as you want. You really want to range over several octaves. So how could I get these octaves? And we've already talked about how you might do that. If I overblow to the higher modes, then I can change the octaves. I already did that without really pointing it out. But here's the trombone, the lowest mode that you can usually easily get is that one. And I can blow up now a series of these various modes and get the overtones, and that lets me move up by amounts that are sometimes an octave, sometimes less, sometimes more. I'm not going to get higher than that, but you might be able to. So that's different by an octave. And then I had an F, which is in between. This is a B-flat instrument, so it's playing a B-flat. So that's the next ingredient that we need, is this concept of overblowing in order to change octaves. And to do that, you're going to be blowing harder and maybe changing your lips in order to dictate what frequency you're telling the instrument to vibrate at. So here, for example, is a little diagram for the flute. The flute, I told you, behaves like an open tube, and so its modes go up like F, 2F, 3F, 4F, 5F. I have here a log frequency scale, so I can compress things down and show you a lot of stuff on a single scale. So here's the octaves going like 1, 2, 3, which display with equal increments because it's a log scale. And so I can use my keys and holes to vary over this range. And then I can overblow and use the same fingering in order to access the second octave. But now the 3F one actually overlaps this, and so you'll see there's going to be 2 ways to play to get that note. And then the 4th highest mode overlaps the 3rd, and the 5th overlaps the 4th, and so on. And so here there will be in these high note regions several ways to get the same note, a different mode and a different frequency. And again, players know how to do that and use these various techniques depending on what they're playing and what fingering would be convenient or not. Now, coming back to the clarinet, we already said that they have same length, but because of the end condition being different, the clarinet plays 1 octave lower than the flute. And we also know that the mode structure goes F, 3F, 5F instead of F, 2F, 3F, 4F, 5F. So we would expect that the overblowing would also be different from the flute, and in fact that's true. So here's what the overblowing diagram looks like now for the clarinet. We do not anymore have the 2F mode or the 4F mode. When you overblow, you have to overblow from here up to 3F, and you see there's a little gap in there that has to be filled with various kinds of holes and keys and stuff. And so that's the reason why, in fact, the clarinet is a more complicated instrument mechanically. It's got to be able to access a wider range of notes because you can't get this region by overblowing. After that, you have overlap here, and you'll overblow to get the 3F mode and the 5F mode. And I don't know whether it's completely obvious, but I think it sort of is, that if you look at the clarinet, there's a lot of stuff here. There's just more holes, more mechanical things than you have for the flute, and that's all to give you this extra, to fill in this extra range here. Well, I'm hammering all this because we're going to work our way to an interesting conundrum that I hope to explore for you. There's often an interaction, I've already said, between the exciter and the wave. And I want to come back now to this theme because it's an interesting one, which I have to say when I started teaching this course, I had not anticipated the need to learn. It's been an interesting expedition to teach a course that's not a field that you're an expert in. You start out with maybe pre-expectations that you already know what you need to know, and you're just going to learn how this applies to simple instruments. And then as time goes along, you realize that it's way more complicated than you thought it was, and there's a lot to learn. And so I'll share with you some of what I've learned now. So the clarinet is like a closed pipe. It overblows to 3F, and that's really true. So we could expect the spectrum now to show only the odd frequency overtones. That is, if I really play the spectrum of a clarinet, I might expect to see 3F, 5F, 7F. I mean, why not? Everything else has come true for the pipe that I showed you before. I'm not a clarinet player, so I'm going to go and get some clarinet recordings that I have made from students in my class. So we might first play this one. And then we're actually seeing the spectrum here in real time, but I have to normalize it so we can watch it. But let's look at this guy. And you'll see that there's the lowest mode. This is 3 times, 5 times, 7 times. But look here. Here's the second mode. And here's 2 times, 4 times, 6 times. And some of these ones that are even modes are really quite big. There's 2, 4, 6, 8. So there's hardly the kind of discrimination against the even modes that I showed you very clearly happens with the pipe. And if we look at this one, which is just a different tone, the same pattern shows up, that even though this is a little bit smaller here, it's pretty big there and there and there, and then they all get to have a very similar kind of intensity. So somehow, this isn't playing out the way we would have expected it to play out. If you read textbooks, you discover that they actually tell you that if you play a clarinet, it will be missing the even-numbered modes, and that's what gives the clarinet its sound. And that's maybe a little bit true, but if you really do the experiment, you find out that it isn't really true. And the first time you do this in a course, and it doesn't play out like you told the students it would, it's a little embarrassing. So I spent some time being interested in this issue. And it took a while to build up some kind of understanding and maybe reading some better books and so on and so forth. So I want to explore that for you now. I mean, one thing I thought was, well, this happened to be a student who was, I would say, not one of our kind of semi-professional music school students. So I thought, well, maybe there's just something wrong with the way that student's playing it. But we had a particularly good student. And so let me get that one. So here was one of my hopings for getting out of this problem. So this is Clarinet Tim. Now you see my problem. It didn't get better when I had a better player. It got worse. So here's the better player, and wow, you know, the even harmonics are really big now. So that didn't work out quite how I had hoped that it would, but I think in hindsight I might have some understanding. If you listen, and I'll just ask you to, if you listen now, these are really firm, robust notes. They don't have any wavering and quavering. So this is a good player. And I think we'll discover that that is of some importance. So let's close that file. And then Alt-Tab back. So what we learned is that the clarinet really has even overtones present. And you could say, why is that? And I asked myself this question. I mean, you say, well, the clarinet body, it's not really a closed cylinder. After all, it's a complicated thing, and there's all kinds of holes you put in, and you did stuff, and it's got a little horn that flares out on the end, and maybe that's the reason. It's not really like a simple tube. Well, maybe it's the reed. I mean, after all, we tested a closed cylinder, so, you know, maybe it's something about the reed. That's another possibility. So I thought maybe we could try an experiment. So we decided to make a tube clarinet. And there's the tube. And down here is the mouthpiece, which I showed you before in the dock cam. And so we'll take the tube and we'll put it, attach it to the mouthpiece, and we will make a tube clarinet. And I'm no clarinet player, but I can get a sound out of it, and I have to practice a little bit. And then let's record that and see what we get. And you see how the logic flows. Got a tube. We already know what that does. It does like the theory says. All we're going to do is add a reed. And let's try to find out how this is going to play out. You already know the various possible frequencies because we did that experiment before. So let's go back over to our recording program, and here is the experiment that we already did, and I'm just going to try and tack onto it some new recordings so we'll have them all there to look at. So first I have to get my sound level. Now the high C squeal, a little dangerous, and it may take a few tries to get a nice one, but let's see what happens. We'll try to ignore the bad ones. Oh, I see. Rats. Didn't turn off like I thought it would, but maybe it doesn't really matter. So I'll have a bunch of sound there. Maybe I should do this one again. I don't really like that too well. So let's see if we can do a little bit better job. Maybe only one bad miscue. So I think that early stuff is the squealing. Let's see what we get. Yeah, so, okay. We started out with a tube, and we know what it does. And there are modes 2, 4, 6, 8. There's the low-lying one, 200. I mean, it's we got the tone that we expected. And you might say, oh, well, if now this mode is present, maybe you're overblowing to that mode. And so let's see how the overblowing went when I went up to the higher one. And then I have to normalize. And you see that it overblows into the third mode up around 600, just like it does with an open and enclosed pipe. But once I have this mode, now here are all the even ones. So this is 600, 1200, 1800, roughly 2400, and so on. So that, now I'll jump back. So this is the lower one. We can see the peaks well enough. So it does jump down from 600 down to here, but now the even ones are present again. So I think that we can make a conclusion from this that it's got to be the reed. It's not that clarinets are funny shaped. It's because clarinets have reeds combined with the cylindrical instrument. And yeah, putting the reed on does make it act like a closed mode, a closed end instrument from the point of view of overblowing. It overblows like the clarinet does. But once you have the mode started, you now get the second and the fourth and the sixth. So the overtones really go like 2F, 4F, and so on. And in the case of the one where we overblow to 3F, you get 2 times 3F, 3 times 3F, and on up. So how does this work? There's a general concept by a researcher named Arthur Benaid, and there's a lovely book, which is, I quote for you here, in which he describes his research over many years. And the concept is that you have feedback and interaction between the exciter, that's the reed, and the resonator, and the effect of what's called nonlinearity in the exciter. This actually will lead us to a new, broader picture of the functionality of a musical instrument and player as entering a kind of holistic, cooperative, and I would say emergent property in which they are one. So I want to spend just a moment talking about this idea of emergence. Mostly what we've been doing today and what most science does is called reductionist science. And you take the view that a phenomenon is the sum of its parts, and you just take it apart. And once you figure out the parts, you just put them together and it works like you expect it to. It's a very powerful traditional approach. It's what's made science what it is, I would say, today. On the other hand, one occasionally encounters, and I think we are beginning to appreciate that one frequently encounters situations which demand us to think in an opposite way, and that is if you have a collection of interacting objects, the behaviors that you get are not necessarily characteristic of any of the individual parts. That is, just knowing what the individual parts do does not always enable me to predict what I'm going to have when I combine them together. So I end up with properties of the ensemble. This seems to be a very fundamental organizing principle in much of nature as one moves to more and more complex kinds of situations. There actually is a virtual emergent science museum now recently online. The creators are very proud of it. It's called emergentuniverse.org. It's intended to communicate this concept of emergence to the public and students and anybody who's interested. So you might like to note emergentuniverse.org if you're interested in going and looking at a website. So I want to say a little bit about this business of nonlinearity. People who are engineers know all this stuff already, and I'm going to give you a kind of simple version which is good enough for our purposes. So the basic idea is if you have some nonlinear device, what you get out is not just proportional to what you put in. So you put something in, and the output here can actually be different. In the case of the edge tone jet, we might think of the input as the jet motion, and the output as the jet flow. And even if the input is something simple, the output can be more complicated. In the case of the beating reed, it's the reed pressure, which could be the input, and the reed position that's flapping back and forth, opening and closing the opening, is the output. In general, these nonlinear effects increase with loudness, and I will say that the difference between my less experienced player and my more experienced player, I think, is related to exactly this issue, and not literally loudness, but a kind of firmness with which you play, how strong the stream of air that you're bringing to the situation enhances these effects that I'm now going to tell you about. So the two particular examples that are important for us are that if you started out with an input that was just a simple wave with a frequency f, you could get out something which is complex, maybe still periodic, but more like our guitar string spectrum with a spectrum of f and 2f and 3f and so on. Similarly, if I put in two of these simple things like f and f prime, I could get out 2f, 3f, da-da-da-da, 2f prime, 3f prime, and so on, like I sketched here. But also, you can generate the sum and the difference frequencies, f plus f prime and f minus f prime. And this turns out to be really important for this effect that we have highlighted in our demonstration. So let's just look at how this might work in the specific case of the clarinet. So I start out, I imagine in my mind of trying to put some simple f in to the nonlinear reed. I blow it in such a way that I imagine that I could perhaps do that. And the reed, because it's nonlinear, actually produces f, 3f, and 5f coming out. And that then gets applied to the resonator. Now the resonator is quite a linear device, and it basically will do what you tell it to do. And so coming out of it will be an amplified version of what you had there, but it feeds back because it's all happening in the same instrument. This guy feeds back, and so we actually end up having, because of this flow, f, 3f, and 5f now put into the nonlinear reed, which in turn will now generate things like 3f minus f, 3f plus f, the sum and the difference frequencies. And if you think about it, 3f minus f is 2f, 3f plus f is 4f. I could also have 5 minus 3, which gives me 2. These differences will generate the even harmonics, even if I only have the odd ones. And so this now gets fed through the pipe and back into here. This thing is now going to be that thing. And at the end of the day, what you realize from this reasoning is that every mode affects the strength of every other mode. It's not just a pipe and I walk up to it as a player and I say, do that. That's not how it works, even with a reed or with lips, because of these nonlinear effects that happen. So every mode affects every other mode. All the modes are now coupled, and they're competing with one another in a kind of negotiation. And in fact, Benaid picked this term regime of oscillation to describe what really happens when you play one of these instruments. And he says in his book, he used the word regime to call up a kind of political negotiation that's taking place between the pipe and the exciter in order to produce the note that you get. It's self-consistent. I mean, at the end of the day, it has to be that the amount of this one that's present generates just the right amount of all the rest of them, that generates just the right amount of thing going on there, and you chase your tail around here. And that's what the player is involved in when they're trying to actually make one of these notes work. Now, I've talked about energy, and I haven't maybe done anything to show you that that might be the case. So do sound waves really have energy? Let's ask a wine glass. So this is a kind of a famous thing that's fun to look at. And we have the opportunity here. Here is a wine glass. This also is a resonating object with natural modes. And we can pretend like it's a string or an air pipe, and we can try to see if we can get it going at one of those interesting modes. So let's see, I want to come to here. And then I want to come over to there. And there is our wine glass. Don't know if we can have, I guess that's going to be okay. And there will come a point where this is going to be loud. So you may want to cover your ears about the time that I decide that I should put my earphones on. But you can see how it plays out for you. So basically what we have is a wine glass, which is sitting back here behind a shield. And it's mounted on a little stand that lets us pick up the vibrations that it's producing. And we have a speaker, which is sort of like one of those speakers that you have in the Michigan Stadium. So it's potent, and it's pointed at the glass. And then we have a way to vary the tone, the pitch, of the sound that's pointed at the glass. So that's the essence of it. And then finally we have a camera, which is the one you're seeing here, and we have a way to essentially make a strobe out of the camera so that we can try to make the behavior of the glass stand still a little bit so you can really see what it's doing. That's the picture. And maybe I can play with the frequency a little bit, so I'll tune it off resonance. So there, it's probably not vibrating much. And I think you can see the glass flexing a little. And maybe I can play with the strobe a little bit. So I think that's pretty visible. Yeah? So you can see, you get a picture of what might happen if I push it a little harder. So that's what we're going to do. I'll count 3, 2, 1, and then I'm going to do it. 3, 2, 1. Yes. So I want really to make it's fun to look at the effects of resonance, that even glasses have this sort of behavior, that they resonate, that they have natural modes, they make sounds. But I did want to make the point that a sound wave really has a lot of energy. And that's of some importance in the clarinet problem, because the clarinet really doesn't want to vibrate at 2F, 4F, 6F. I mean, it doesn't want to do that. So the reed draws energy from the modes 1, 3, 5, where the pipe really does want to do that. And through the nonlinear mechanism, it gets enough energy to force the pipe to do what it wants it to do because of the nonlinear effect. Now there is an even more dramatic version of this, and I want to end up talking about that. It's sort of intellectually, yeah, we're almost done. This is intellectually, I would say, not, how should I say, it's intellectually dramatic, but less showy. So a stronger example of these concepts of the regime of oscillation and the emergent behavior are what are called pedal tones for brass instruments. If you look at the actual lowest mode frequency, you find that it's too low to build one of these harmonic series that you need for making a sustained note. And it makes the fundamental very, very hard to play. Skilled players can do it. It's called the pedal tone for the case of the trumpet and the trombone. And here I just illustrate how this looks with numbers for the trombone. So the normal mode that you play is B2 flat, which happens to be about 116 hertz. And if you play up the series like I did for you, you play to an F, 1 octave higher, a B3 flat, a D4, F4. And if we didn't think about it very much, you might think that this would have to be 1, 2, 3, 4, 5, but it's not. This is actually 1.5, 2, 2.5, as the numbers you multiply to get the actual frequencies of the notes you're playing. And you'll say, well, that doesn't look like a harmonic series, and it's true. The actual lowest note, the bottom of this series, it turns out to be B1 flat, which is 58.3 hertz. And now all of these notes link back to B1 flat as F, 2F, 3F, 4F, 5F, 6F. Now the normal mode that a trombone plays is exactly B2 flat. In principle, the trombone will play 1 octave lower in the pedal tone. But in practice, it's almost impossible to make it do that unless you're a very good player, because if you think about it, it turns out that the lowest mode is actually not at the right place for the series. there, it actually has a frequency which is more like 44 hertz. It has to do with the details of the way the mouthpiece and the bell and the tube interact. So when you're trying to play it, your lips go looking for this lowest thing here, but it isn't there. It doesn't exist. The pipe won't do it. On the other hand, if you try to actually make it blow at its true lowest mode, all the rest of the things which would suck up energy are inconsistent with it because they aren't any particular kind of a multo with respect to that. Nonetheless, it's a fact that experienced players can do it. And let me just see what we have. Yeah, so let me tell you what Benaid would say about this, and then we'll listen. So Benaid would say that the lip reed instability is essential for getting the pedal tone, and you kind of know how the numbers already work. The resonator has the higher harmonics at 2F, 3F, 4F, 5F, and if I can somehow get some energy into those modes and draw them into the lips, that energy can be used to generate the overtones, to generate the sum and difference frequencies. 3F minus 2F is F, 5F minus 4F is F, and all the various possibilities. And so there's energy available if the lips can figure out in their nonlinear way how to do it. But it's pretty hard. This is different than the clarinet case, where the mode I want is already available to me, and then once I get it going, the even harmonics fill in. This is a case where you need to have the thing going in order to have available the modes that are going to give you the energy to get it going in the first place. And that's why when a player like me tries to do what I know how to do, which is to generate, I know exactly what to do. I move my lips in ways that search out those modes that really exist. So I try to do the same thing to get the lowest one. I mean, I know what I'm supposed to do. I'm supposed to loosen my lips and go for lower notes. And it's not there. And it's not that my lip muscles are bad. I showed you that I can play the higher ones. I literally don't know what to do. I think it's calling for something really quite new. Now, we had in our class some trumpet players one year and a trombone player named Joey Munoz. And they brought their instruments to class. Maybe we might first listen to Andy. So the first one is Andy getting the pedal tone on a trumpet. And the second one is Andy playing a flugelhorn, which he brought. I seem to be getting some feedback from someplace, which he brought because it's easier to get the low note. And so right in here, something interesting happened, which had never happened to him before. So let's just listen to this. You see, it wasn't easy for him to get notes. So play it once more. You hear the extra come in there at the end? So let's take now a little look. And then I have to normalize these guys. So this now is the lowest mode. So this is that one that's hard to get, and that's the spectrum. You'll notice they go out pretty far. I'm running this out to 5,000. So there they are. And then if we look at the flugelhorn, which easily gets the lowest note that he was trying for, there is its spectrum. There it is, like that. And this is down around 100. And what happened was, when we got that kind of flatty sound, you see I now have a mode that's sitting here at half of that. He said it had never happened to him before playing the flugelhorn. I think it's because he was already trying hard doing that thing that you have to do in order to make the trumpet get its pedal note. And this, I think, that thing you hear is the pedal note of the flugelhorn, which happens to be the same as what you get from a trombone when you play the trombone for the pedal note. And so now I want to do you some trombones, and then we'll be done. So let me close that and come back to trombones. So I want to listen to Joey. Oh, sorry. Trombone. Open. There they are. We can blow them up just a little bit. So Joey brought in two trombones, one of which was sort of a trombone like this, maybe a little nicer. And then he brought in one which was sort of had a bigger bell. And he said, this one's more robust with the bass, easier to play this lowest note. But first, he picked up my trombone after I went trying to get the lowest note. He just picked it up and played the first note, and then he picked up the second trombone and played, and then he picked up the third trombone and played, and this is what we got. So that first note is this trombone doing its thing in the hands of somebody who knows how to somehow get the thing going when it isn't going yet, but it needs to be going in order to go. I mean, that's what the lips have to do, and it's completely different from what you have to do for something else. If I look at the spectrum, let's just normalize again so that they show kind of pretty. And actually, I'm going to increase the range. Well, maybe not quite yet. So like we saw for the flugelhorn, here's the lowest one. That's the pedal. That's the tone that defines the pedal tone. The instrument does not want to go there. And then there's a zillion harmonics going up higher. And now it's kind of interesting to look at this one, which has this deep sound. You might somehow imagine, and I did initially, I thought, oh, that must be because he's getting a larger amount of the lowest one. But it's not true. In fact, it's a little smaller than in the other ones that you see. I thought about this a long time, and it finally occurred to me that maybe I ought to be paying attention to all the rest of the energy in the spectrum, which is distributed in all these other modes. And so I want to just look at them over a little bit higher range. So let's go out to 10,000 hertz so we can see the spectrum a little bit better. And again, we'll normalize these. So there are lots and lots of modes. And in fact, you can see that the trombone is producing a lot of stuff. I mean, there must be 10 of them, 20, 30, 40, 50, 60. They're all the way out to 6,000 hertz. That's what's going on, which makes the instrument have a kind of brilliant tone, if I could put it like that, even though it's very low. And now, if we look at the difference between, say, that and that, your ear doesn't detect much difference, and indeed, they're pretty similar. Here's the one that really sounds deep. It's a subtle difference, but the difference is all up in here. It's the relative amount of stuff down there and stuff down there that's affecting your sense, your perception of how deep the note sounds. I just play it once more. Compared to there's no doubt we'll all agree what the fundamental is, but this one somehow sounds deeper. And the difference is because of the distribution, that it's got more stuff at the low frequencies, but it's not the lowest one that matters. It's the whole spectrum. And that then takes me to kind of my last point that I'd like to make. And that is that there are other emergent aspects that we could think about. One is the brain's sense of consonants. We don't really have time to talk about this, but I'll just say, as I did at the very beginning, it involves chords that are built out of numbers with frequency ratios of low whole numbers. So a major triad, for example, has a ratio of 4 to 5 to 6, and a minor triad, which definitely sounds different to your ear, is 10 to 12 to 15. The early ideas about what's consonants and what's going on in your head came from Galileo, who emphasized these kinds of relationships. And nowadays, the neuroscientists would still think that this wasn't stupid, and what has to be done is to understand in detail what the brain does when it listens to 3 notes together. We have also to think about that, but I mention all this because it's very clear that we are not simply focusing, as we listen to the note, on the lowest pitch determining note. Your brain is taking in the data all the way up, all those almost 100 harmonics and their distribution, and inferring something about that distribution back to the fundamental and feeding your mind some sense of, wow, that's really deep. And so it's complicated. And then how about when you actually have an audience? So that the brain of anybody sitting in the audience is doing this stuff, but the audience altogether is having some kind of emotional reaction to the music, and that is surely creating something that feeds back to the performer. So at the end of the day, this phenomenon we call music, broadly understood, is an emergent activity at all levels of complexity, from the simple physical level that we've been talking about with musical instruments, which is not so simple, up to groups of human beings, so that an actual performance is a very cooperative enterprise with lots and lots of different kinds of feedback going on. So I'm done now. Thank you very much.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.